Welcome my dear learners for this course on mechanical vibrations. In this module 2 we were discussing on forced vibration. In our previous lecture we have began discussion on forced vibration and also we have discussed the system response for an vibrating system subjected for harmonic external excitation. Now coming for forced vibration, there should be an excitation which keeps the amplitude of vibration constant. This excitation must be continuous. Now the excitation need not be external always. There might be internal excitation also which causes forced vibration, which I explained in our previous lecture. If you want to list some internal excitation forces, the internal excitation might be because of thermal effects, might be because of bearing defects, and might be because of resonance, and also I have explained it might be because of rotating and reciprocating unbalance. So one of such case, that is the forced vibration set up due to rotating or reciprocating unbalance, is the topic of today's interest. That is, in today's lecture I am going to address the rotating and reciprocating unbalance, which means I am going to derive an expression for system response for a system which is subjected for rotating and reciprocating unbalance. That is, today we are going to discuss the system response of rotating and reciprocating unbalance. If the masses are not properly balanced in the rotating elements as well as in reciprocating machines, that will set up forced vibration. Now any machine containing rotor as one of its part is called as rotating machine. If a mechanical equipment contain rotor as one of its parts, then it is called as rotating machines. Now the axis of rotation of the rotating machine and also CG, that is center of gravity of the rotor, if these two does not coincide, then there exists an unbalance in the system. The distance between the axis of rotation of the entire machine and the center of gravity of the rotor is known as eccentricity. The mass of the rotor which is placed at eccentricity is known as eccentric mass. Now this eccentric mass will cause unbalance in the system. So in order to analyze that, let us consider a figure like this. Let us have a foundation. Let us have a foundation like this, upon which I will consider spring and dashpot. Spring and dashpot. Dashpot represents the resistance for vibration and spring represents the stiffness, that is elasticity of the system. Now upon which we have an rotating machine mounted. Let us say we have a rotating machine like this. And this is displaced vertically upwards x. As I said, let us have the axis of rotation and the eccentric mass which is placed, that is the rotor which is placed at a distance e from the axis of rotation, that is the distance between the axis of rotation of the entire machine and the center of gravity of the rotor. Let us take here. Now let us have the eccentric mass as m0. Let me use different chalk for better understanding. Let us have m0 as the eccentric mass. Now let us take the reference and we have the eccentric mass here. So since this is rotating mass, the force generated will be centrifugal force. This you people already know. The force generated will be centrifugal force, that is m omega square r. What is the value of r here? The value of r is eccentricity, the distance between the CG of the rotor and the axis of rotation is termed as eccentricity E. Hope it is clear. The mass of the machine including the eccentric mass, let us take it as small m, whereas the eccentric mass can be taken as m0. The distance between the axis of rotation and the CG of the rotor, that is eccentric mass, be eccentricity E. Now the formula for centrifugal force is known for us, that is unbalanced centrifugal force is mass is m naught omega square. What is the radius of rotation? Eccentricity E. Right. So what I am defining? I am defining mass m, which is mass of rotating machine, including the eccentric mass m naught, including the eccentric mass m naught. So what is m naught? Eccentric mass. Here itself I have defined. Now E is the eccentricity. So eccentricity is the distance between the axis of rotation and CG of the eccentric mass. Let the eccentric mass makes an angle of omega t with respect to the reference. Let the angle made by the eccentric mass m naught with respect to reference be omega t. Now we know that since it is displaced, the entire mass is displaced vertically, the force Fc can be resolved into two components, correct? One is horizontal component, another one is vertical component. But here if you carefully observe, since the mass is displaced vertically upwards, the concern for us is the vertical component, not the horizontal component. So what is the vertical component of the force acting? Due to eccentric mass m naught will cause the unbalance in the system, which is nothing but causing the internal excitation for forced vibration. Now what is the vertical component of force? The vertical component of force is the excitation force, which is nothing but m naught omega square E into sin omega t, correct? So this is the vertical component of force. M omega square r is the Fc, vertical component is sin omega t. Now at any given time, what is the displacement of m naught? At any given time, the entire mass is displacing by x from the reference, but the mass m naught, that is the eccentric mass m naught, is already situated at a distance how much from here? So what is the overall displacement of this mass m naught at any given time t is the question. From the reference, the rotating mass is displaced by an amount of x, whereas when the mass is displaced by an amount of x, what is the displacement of m naught? The displacement of m naught will be x plus, it is already displaced by an amount E sin omega t. So this vertical distance is how much? This is eccentricity. So vertical distance is how much? E sin omega t. So therefore at any given time, the displacement of mass m naught will be x plus E sin omega t. Now the displacement of mass m naught at any given time will be x plus E sin omega t, correct? What I mean to say is that we have the displacement x, the mass is already situated here, that is m naught, this distance is already known for us, this is E sin omega t. So therefore the displacement of m naught is x plus E sin omega t. Now let me call that as y. Let me call that as y, which is equal to x plus E sin omega t. Now we know that for equilibrium, sum of forces must be equal to 0, right? Now for equilibrium, sum of forces must be equal to 0. What are the forces acting? One is inertia force, second one is damping force, third one is spring force. So if I write them, the first one is m. So mass m is nothing but mass of rotating machine including m naught. But the mass m is displaced by x, whereas m naught is displaced by y. So therefore, the inertia force of machine which is displaced by amount of x will be m minus m naught. M minus m naught, because m is including m naught. So therefore, remove m naught from it, into what? X double dot, that is d square x by dt square. So inertia force of rotating machine excluding the eccentric mass m naught, plus now m naught is displaced by amount of y, that is m naught d square y by dt square, that is acceleration. Mass into acceleration is inertia force, plus damping force is cx dot, plus spring force is kx. This must be equal to 0. Hope this is clear. Inertia force of rotating machine excluding the eccentric mass m naught, inertia force of m naught, damping force and spring force. Sum of all these must be equal to 0 for equilibrium. Now if I simplify this, what I am going to get? M x double dot, correct? So m x double dot minus m naught x double dot plus m naught into d square y by dt square, where y is x plus e sin omega t. So substituting which, I will get d square by dt square of x plus e sin omega t plus cx dot plus kx is equal to 0. Now simplify this. If I simplify this, I will get mx double dot minus m naught x double dot plus second derivative of displacement is acceleration plus m naught x double dot plus differentiation of this twice. So E is constant, that is m naught into E. Now the first derivative is cos omega t into omega. If I differentiate cos omega t into omega again, I will get minus omega square sin omega t. Now this is plus cx dot plus kx is equal to 0. Now these two will get cancelled. Now if I rearrange the terms, I will get mx double dot plus cx dot plus kx is equal to m naught e omega square sin omega t. Got it? Now what is the excitation force? As I said, it is m naught e omega square sin omega t. I got it. Right. Now compare this with the forced vibration equation. So from forced vibration equation, that is equation of motion, from equation of motion of forced vibration, what is that equation of motion of forced vibration? It is mx double dot plus cx dot plus kx is equal to what? F naught sin omega t. Correct? Now compare these two equations. So compare the equation what we obtained and compare equation 2. Comparing equation 1 and 2, we get comparing equation 1 and 2, we will get the magnitude of force F naught, that is the amplitude of force, will become m naught e omega square. M naught e omega square. Now for equation 2, we know what is the system response. That is what we have derived in our previous lecture. Recall the expression what we have derived for equation 2 in our previous lecture, the system response, and solve further. So for which I will recall the magnification factor or amplitude ratio, which you people already learned in our previous lecture. So therefore, recalling the magnitude ratio or the magnification factor. So recall amplitude ratio Recalling amplitude ratio, we have A is equal to F naught by K, which is nothing but static deflection, divided by what we have, square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. This is what we had, right? Now substitute F naught here and simplify. If I substitute F naught, so what I am going to get, if I substitute F naught, that is the amplitude of vibration A is equal to F naught is m naught e omega square. F naught is m naught e omega square by K. What I will do, I will multiply and divide by overall mass m. I will multiply and divide by overall mass m for simplification, into we have 1 divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square, right? Now what I can do, K by m I can write it as omega n square, correct? K by m I can write it as omega n square. So if I simplify further, what I will get, A is equal to m naught e by m into omega by omega n whole square into 1 divided by root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square, correct? Now which is nothing but, I will get the equation in the form A divided by m naught e by m. A divided by m naught e by m is equal to omega by omega n whole square into, I can write this as 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square to the power of what? It is 1 by square root, right? So if I take it to numerator, it will become minus 1 by 2. Very, very important. Minus 1 by 2. So I got the equation for amplitude. Now what is the system response? We know that system response X is given by complementary solution plus particular solution. What is particular solution? We have already learnt in our previous lecture. The particular solution is nothing but amplitude of vibration times sin omega t minus phi, correct? Recollect from our previous lecture, sin omega t minus phi, sin of omega t minus phi, where A is amplitude of vibration. Particular solution is amplitude of vibration times sin omega t minus phi, where phi is the phase difference between the excitation force F and the amplitude of vibration, correct? Now if I substitute, the complementary solution is nothing but the transient part, which I clearly discussed in our previous lecture. So therefore complementary part of solution is nothing but solution of underdamped vibration system. Now the system response will become what? X is equal to, complementary solution is nothing but solution of underdamped vibrating system, which we already know. It is given by a constant C4 e to the power of minus zeta omega nt into cosine of root of 1 minus zeta square omega nt plus phi 2, correct? So this is solution for complementary part. Now what is solution for particular part? This is continued here plus plus particular part is A sin omega t minus phi. What is the value of A? Amplitude of vibration here. That is A is equal to m naught E by m divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square under the root A into sin omega t minus phi into sin omega t minus phi. So I substitute for amplitude of vibration from the equation which we have derived. So this is the system response for rotating and reciprocating unbalance. I will discuss why this is a system response for reciprocating unbalance also. Now we have derived expression for system response of rotating unbalance, which is given by this equation. This is complementary part of solution and this is particular part of the solution, and this is the overall system response. Now the careful observation is that at resonance, what is the amplitude? Amplitude will be maximum at resonance, correct? So therefore maximum amplitude of vibration will become what? Maximum amplitude. Amplitude will be maximum at resonance, that is omega is equal to omega n. Hence what is the value of A max for this problem or for this discussion? A max will be what? Put omega by omega n as 1, so this will become 1, so 1 into this will become 0, 2 zeta, 1 into 2 zeta, that is 1 divided by square root of 2 zeta whole square. So square and square root will get cancelled. I left out with A max as m naught E by m divided by 2 zeta, correct? M naught E by m divided by 2 zeta. Whereas the phase angle formula remains same. What is the formula for phase angle? Which we have already discussed. The phase angle tan phi is equal to 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So this is the result of rotating unbalance in the rotating machines. Let me pause this video for a while so that you people can copy it down. Later we will discuss reciprocating unbalance. Now moving ahead for reciprocating unbalance, So in order to understand the reciprocating unbalance, let us consider an IC engine. If I consider an IC engine, so how it will be looking like? An IC engine can be drawn like this. So let us have the foundation, let us have spring and dashpot, let us have the body like this. So let me draw a free and rough sketch of an IC engine like this. Now we have the rotating part here and we have the reciprocating part, piston. Piston is reciprocating inside the IC engine and we have crank and connecting rod. Let us have crank and connecting rod like this. Let L be the length of the connecting rod and eccentricity E be the length of the crank and m0 be the mass of reciprocating part. m0 be the mass of reciprocating part. So let us consider an IC engine having the reciprocating mass of the piston as m0 as shown in this figure. Now this piston will reciprocate to and fro, correct? Now the careful observation reveals that the unbalanced force generated can be written as inertia force due to reciprocating mass m0 is approximately equal to F is equal to m0 E omega square sin omega t plus E by L times sin 2 omega t. So this is the inertia force due to reciprocating mass m0 in the reciprocating system, that is IC engine, which I have considered for analysis. Now the value of E is very small compared to L. So therefore the ratio E by L is very, very small. The ratio E by L is very, very small. So therefore we can neglect the second harmonics. So therefore m0 E omega square into E by L sin 2 omega t can be neglected. The second harmonic m0 E omega square into E by L sin 2 omega t can be neglected. So hence, what is the excitation force you will get? The excitation force will remain same, m0 E omega square sin omega t, which is same as the excitation force for rotating unbalance. So therefore the discussion what we had made for rotating unbalance holds good for reciprocating unbalance also. So since the excitation force is same for both the cases, the discussion what we made for rotating unbalance holds good for reciprocating unbalance also. Hence the solution of rotating unbalance holds good for reciprocating unbalance also. So therefore, what is the system response of reciprocating unbalance? It is same. This is the system response of reciprocating unbalance as well as rotating unbalance, and this is the maximum amplitude which takes place at resonance. So this completes our discussion on system response for rotating and reciprocating unbalance. That's all from this lecture. Thank you all.